Welcome to Meteorology 101. Visit our website at meteorology101.com and like this video, share, and subscribe. That's the only way I can keep these videos coming out, is if I get the views. In this video, I'm going to talk about the Earth's atmosphere. Meteorology and the Earth's atmosphere. Meteorology is a science that deals with the phenomena of the atmosphere, especially weather and weather conditions. So a lot of people get that confused sometimes. Meteor, they think space weather. That's a completely different thing. This is meteorology, so it is with weather and weather conditions here in our atmosphere. Some history on meteorology. Weather instruments. Around 340 BC, Aristotle wrote the first weather book, Meteorologica. In the book, Aristotle identified such terms as clouds, rain, snow, wind, and hail. Primary method of forecasting weather early on was pattern recognition by monitoring clouds, temperature, and moisture. So if you look at the clouds today, if you identify your cloud types, you can see when cirrus comes through, and then you'll get a mid-level, then a lower level. You can watch the patterns happen. You can see if you have a cold front approaching. You can judge if you're going to have rain within the next few days or not, just by watching the clouds. Weather patterns are particularly helpful for sailors since their lives depend on the weather. The sailors, all the ships in the sea, that's huge for the Navy. The Navy has their own, they have a weather station on every ship. They have buoys out in the ocean, and the Navy creates their own weather models. So they're really huge on weather. Same with the Air Force. Weather instruments in the 1500s, the water thermometer was invented by Galileo. These were bulbs with liquids of different densities that were floating in a clear liquid, and when that clear liquid changed its density based on temperature, then those different bulbs would float, and that would tell what the temperature was. So a pretty neat invention. How accurate that was, I don't really know. Thinking about purchasing one. Maybe you'll find out. And the mercury barometer. So Evangelista Torricelli became the first scientist to create and sustain the vacuum and to discover the principle of the barometer. Torricelli realized that the variation of the height of the mercury from day to day was caused by changes in atmospheric pressure. There actually was a pressure reading measured in torr. That was the unit of measure. Now we use millibars and inches of mercury. And for more information on atmospheric structure, visit meteorology101.com/atmospheric-structure. That goes in. There's an article that goes into detail about the atmospheric structure of every planet. Weather instruments, with the thermometer, the Fahrenheit scale. That was based on a German, proposed by a German in 1724, and I guess it was invented between 1686 and 1736. The Celsius scale was invented by Anders Celsius, a Swedish astronomer, in 1742, and he named it the centigrade scale. The Kelvin scale was developed by a British inventor and scientist, William Thomson. So the Fahrenheit scale, that was the one. That's the one we use today in America. Weather charts, pretty much weather worldwide uses the metric system, so it's all done in Celsius. Fahrenheit is 32 degrees is freezing, 212 degrees is boiling, the boiling point of water. Celsius 0 degrees is the freezing point of water, and 100 degrees is the boiling point. Kelvin, that's a pretty big scale, but minus 273, I believe it is 273 degrees Celsius is 0 degree Kelvin. 0 degree Kelvin is when all molecular activity comes to a stop. That's when that is completely frozen. That's the only thing I really remember about the Kelvin scale. We don't really use that in a whole lot of stuff. Weather equipment, this is more of the 1920s. Norwegian meteorologists developed theories of fronts and air masses. Not much equipment here, but what they were using surface observations based on temperature and wind direction, and that would give them the determination if an air mass was coming through, a cold air mass, a frontal system. If you took frontal passage, you would notice a significant change in wind direction and maybe a significant drop in temperature. So still today, even looking, like I said, looking at the clouds, you watch the cirrus clouds come through, and then you'll watch the clouds drop. You can watch it as a pressure system or a air mass is pushing through, if it's a frontal system, pushing through the area just based on the cloud types. So once you take frontal passage, obviously the weather associated with frontal passage, you can tell if the weather is, if that frontal passage, how strong it is. If it's a steep slope front, a shallow slope front, then you'll have the weather if it's pushing through fast and the weather being at and ahead of the front, or pushing through slow and being at and behind the front. That's just different ways to tell what type of air mass you're dealing with and what's pushing through your area. Other weather equipment in the 1940s, the radiosondes, weather balloons were invented. This was the first 3D picture of the atmosphere, more of a cross section than a three-dimensional picture. When the weather charts were developed, when they used the radiosonde, they send up into the atmosphere, sends data back. There's mandatory levels. The surface, to get a surface chart, 850 millibar level, 700, 500, 300, 250, 200, and you can go up to 100 millibars. This thing actually will send the data back to wind direction, wind speed, temperatures, dew points, and then all that data is actually sent back in a code. It has to be decoded and then put on a chart, which is the SCU-T chart, and then you could do a couple calculations on that would show you the stability of the atmosphere, what your cloud heights are going to be based on a convective temperature, what your cloud heights would be on your lifting if a cold front comes through and the moisture was pushed up, where those clouds would form. So there's quite a bit you could tell off of a SCU-T chart. So that is 1940s that was developed. And everybody remembers Roswell. That was a weather balloon, right? Okay, weather equipment in the 1950s, the first computer models were developed. Obviously terrible graphics. These are pictures of the first ones. And then 1960s satellites were invented. So the computer models have come a long way. These computer models that they're showing in the 1950s, that was basically, temperatures, just a computer extrapolation of temperatures, pressure, just to give them an idea of what systems were out there and what was coming through. A lot of people use models today. They pretty much forecast right off the models. They read them. Just here, the model says it's going to rain Friday. They show a pressure system, a frontal system going through, moisture, lift, instability, everything you need for a thunderstorm. There's going to be a thunderstorm, and then that day comes, thunderstorms don't happen. They don't verify the models. The models are used as a tool, not as a 100%. That's what's going to happen. And as far as technology has come, we can only accurately forecast the weather only a couple days out, really. Satellites are your big helper on identifying surface features, then what's going on in the upper levels with water vapor, where your ridges are located, troughs, your dry areas. The satellites was a big turning point, along with the models. It was a big turning point for weather. So the current weather models, with the rapid increase of computer technology, we have very sophisticated weather models. I find that most of your upper air models are more accurate than the surface, because the surface is, with the friction, mountain ranges, a lot of stuff playing a part, and depending on the levels of moisture at the surface, frictions from the surface, You get a lot of variables on the surface chart. So the upper picture here is the jet stream. I believe that's at 300 millibars. That's showing a jet stream coming down, basically getting ready to form a cutoff low right there over the four corners. That's pretty typical for the southwest United States. If you do get a long wave trough that comes through like that, the jet stream can't make that turn, so it just starts overshooting and leaves an area pretty much right around the four corners. It'll just sit there, and then it'll fill and just dissipate. The jet stream will drop down, and then it just, like I said, it just overshoots it and then cuts off and goes through, and then you have just a major short wave basically that shoots through to the northern United States. So the lower chart that shows precipitation, which would be estimated for a 6-hour period prior to the valid time of this chart. So it shows the pressure systems, what they're estimated to be, and then how much precipitation would have fell in the last 6 hours. So these charts are actually measured in millimeters. So you take the millimeters, convert to inches, and then inches that's how many inches of rain you would get for rainfall, and then you would have to convert that to snow. So snow is 10 to 1. If you got 1 inch of rain, that'd be 10 inches of snow. So you can use these models. Like I said, they are a tool. They're not, okay, if you got an inch of rain going to fall, then you can't say, yep, we're going to get an inch of rain. These things change every day. Every time they do a model run, they're updated, and then they change, and then your whole forecast changes if you're forecasting from models. That's why you have to know. If you go back to those SCOOTs, you can pull up what is the moisture in the upper levels, what system's moving through, is it going to dry out, is it going to become more moist, then you can use these tools to estimate actually what is going to happen. So the Earth's atmosphere, one, provides the Earth with water and gases to sustain life, and then protects the Earth from deadly radiation from the sun and debris from space. So a lot of debris comes from space through the atmosphere, burns up in the atmosphere before it ever hits the Earth, and that protects us. So it keeps us cool during the day and warm at night, the greenhouse effect. So without the clouds in the atmosphere, we would pretty much be freezing at night and burning up during the day. So that's why it's so important with the ozone layer and all that. And we'll get into something like that later, but we're not going to go into global warming and all that stuff. So right now, the Earth's atmosphere protects us from the sun and the bitter freezing cold at night. The Earth's atmosphere is about 99% of the atmosphere lies within 19 miles of the Earth's surface. 19 miles from the Earth's surface is pretty much the atmosphere, the Earth's atmosphere, the thin blue line you see in the picture. Atmospheric gases, nitrogen 78%, oxygen 21%. Those are pretty much the two that the main components in are air and water vapor. H2O is variable concentration. You can see I put a water vapor satellite, and you can see all the different levels of moisture throughout the atmosphere just based on that satellite. So higher concentration of moisture in the tropics, lower toward the poles typically, lower, higher in the tropics to near the surface. So cold air doesn't hold moisture, warm air does. So that's why you have more moisture in the tropics. The atmosphere actually is a lot taller a lot further up along the equator than it is in the poles because of the hot air and the cold air. The higher heights in the warmer latitudes and lower heights in the colder latitudes. And the phase changes are important source of latent heat and the greenhouse gas. So the phase changes are from water going from a liquid to a gas, and then from a liquid to a solid to a gas, and then you're going to actually evaporate ice and go straight from a solid to a gas. So sublimation. Atmospheric gas is carbon dioxide. You're going to 0.037% of the atmosphere is carbon dioxide. So CO2, just the big main greenhouse gas. That's has the ability to absorb outgoing radiation. back to the greenhouse effect, you know, how the carbon dioxide affects us, natural sources, decay of vegetation, volcanoes, respiration of animals, breathing. So, man-made sources burning fossil fuels. So, CO2 levels. Look, the Earth is a balance. It's constantly balancing itself. Same thing with that's with the atmosphere. Cold over warm, warm over cold. You know, cold over warm is an unstable environment. Cold air wants to sink, warm air wants to rise. So it's constantly trying to balance that out. That's where you get the instability. You know, if you have the moisture, you got lift, you have thunderstorms, you have, you know, that's where we get weather. It's just a natural occurrence. Volcanoes, if a volcano erupted, that put out more CO2 than I think man could think of for a long time. Burning the fossil fuels, I think anything we contribute to that issue, I think it's minimal. So there's my stand on it. Vertical structure in the atmosphere, density equals mass over volume. How much mass is is in a volume of, in a certain volume, that's going to give you your mass. There's a number of particles in a given volume. If you take a box, you put so many particles in there, that's going to, you can measure the density of that area within that box. Pressure is how much force is over that area. So gravity obviously is our force. So you take those particles, put it into a volume of air, put the gravity pressure on it, now how much with the mass, and then the gravity pushing down, giving you that pressure. So basically the total weight of air above you at any given point. At the Earth's surface, all the air, the Earth's atmosphere is above you, so you have a higher pressure. But if you're in an airplane, now you have atmosphere above you and below you, so now you have a lower pressure above that, where you are. So if you took 10 square feet of area, captured all the air above it, and weighed it, it would weigh about the size of a large elephant. We have blood pressure, so we don't know, our bodies are pressurized, so we don't notice that pressure. But that's how much atmospheric pressure is in a 10-foot square area. Pressure and density, obviously, as you go up in altitude, pressure decreases. You have less molecules above you, so less mass, so less density. So density is great and pressure are greatest near the surface. Both decrease quickly at first as you go up in altitude. Average sea level pressure is 1,000, 13.25 millibars to 9.92 inches of mercury. So this is your average, and any pressure above those readings is considered high pressure on a weather chart. Any pressure below those readings is considered low pressure on a weather chart. That's where it becomes the big player in the weather charts, how we're reading it, what we're interpreting as low pressure, high pressure, and then what we should expect, you know, from weather, from those pressure systems. Atmospheric structure, there are 4 layers, 3 pauses. Pauses cap layers in areas where temperature stays the same with increasing height. So we live in a troposphere. Our temperature naturally decreases with height. Then we hit the tropopause, and there's no change for the thickness of the tropopause. No change in temperature. And then we hit the stratosphere, and then there's an increase in temperature with height. Then once again we hit the stratopause, no change in temperature with height. Then we hit the mesosphere, and then we have another decreased temperature with height. So naturally, the cold over warm. So if our temperature at the surface is warm, we get cold as we go up. We have cold over warm. We're in a naturally unstable environment. That's the part of the environment we live in. Part of the atmosphere we live is unstable. Stratosphere is stable. Mesosphere is unstable. Thermosphere is stable. So the mesosphere, yeah, there are some clouds in the mesosphere that can form, but they're not weather producers. Nothing significant. The troposphere, where we live, that is where all the weather happens for us. The top 11 kilometers. Or the bottom 11, the first 11 kilometers is where most of your weather happens. Isothermal. The isotherm, it's a line. Isotherms are lines of equal temperature. Isothermal means there's no temperature change. So lines of equal temperature. You see an isotherm usually a dashed line on a weather chart. That is lines of equal temperature. Then your lapse rate, real quick, isobars are lines of equal pressure. So if you look at a weather chart, isobars are the lines of equal pressure. Then that's where you could tell where your high pressure, low pressure systems are. So lapse rate is how much the rate at which the temperature changes with height. And that's how we get with the radiosonde. We send the weather balloons up. That radiosonde sends the information back, and we get that information. We know what our rate of change of temperature is per 1,000 meters. So your average, if it gets into this, average is 6.5 degrees Celsius per 1,000 meters. That's the average temperature, the lapse rate. And once again, all weather takes place in the lowest 11,000 meters, 11 kilometers. So, and then it is capped by the tropopause. So, once that temperature doesn't change with height, then that's where you get into a more stable area that caps all that weather to the below that. So, you can get, say, a thunderstorm that builds up, cumulonimbus cloud shoots all the way up, hits the tropopause, and then that updraft is so strong it pushes into the tropopause, and then that's where you get the overshooting tops from those thunderstorms. And you're typically into a supercell, or you could be into a severe thunderstorm, or you just get the overshooting tops. You have a strong enough updraft, depending on the moisture, how much moisture you got, how strong that updraft is to pull that water together, pull that water up above the freezing levels. It freezes, collides, becomes bigger, gets too heavy, falls below the freezing level, starts to thaw, and then more water collides with more water drops. Updraft comes along, pushes it back up, refreezes. Hail gets bigger and bigger and bigger. Now that's a whole other subject. So, but you can get those updrafts that will shoot all the way above that tropopause and give you overshooting tops. You can have thunderstorms reach pretty significant heights. Alright, atmospheric temperature. This was Scooty I pulled from Wilmington, Ohio. If you look at the black line is temperature, green line is dew point, and you can see the spreads pretty dry on the mid levels, and then a little bit of moisture at the top. You see about 450 millibars. Down at the bottom, you got a little bit of moisture. You have an inversion on the temperature side. So increase in temperature with height is an inversion. So that would cap off any moisture at the surface, anything going on at the surface. Radio waves would hit that inversion, go way out. You could communicate a lot further during that situation. This is most like a 12Z chart, which is about 7 a.m. So you have subsidence at night. That cold air comes down, it caps the top, just right there above the 1,000 millibar mark, caps that off, and then holds everything to just below it. So if you were to blow up a bomb, that noise would travel way further than the blast would travel way further than it would if you didn't have that inversion. So you have a isothermal layers. Those are increased temperature with height. There's one, and there's the other one. The one at 200 millibars at the top, that would be your the top of your that'll be your tropopause. That would be basically, you look at the temperature right there. There's no increase in temperature with height. That line is a temperature line. It's just following straight up at an angle. So that's your tropopause. The Scooty charts, like I said, you can get instability indexes. Several of those you can see what your winds are doing with height. If they're varying with height, increasing the speed with height, backing with height, and there's so many different equations you could do on this chart that will show you the stability of the atmosphere where that balloon was released. Stratosphere, the stable layer. Temperature increases with height as temperature increases with height, you have warm over cold. So that is a stable layer. Warm air wants to rise, cold air wants to sink. So there's nothing really happening there. On an unstable layer, cold over warm, is where we live, the troposphere, then we get the temperature decreases with height, and you have cold over warm. So cold air wants to sink, warm air wants to rise, and then that's when you get the mixing. That's an unstable environment. So the stratosphere is a stable environment. The temperature, definition of temperature inversion, a layer in which temperature increases with height. What causes the warming in this layer? The ozone layer, and it absorbs the ultraviolet radiation from the sun. So the stratosphere protects us, absorbs that radiation from the sun, and gets pretty warm. Mesosphere, that is an unstable environment, but like I said, you do have some clouds up there, but you're not going to have convection and all that stuff in the mesosphere because there's not enough moisture getting up to that layer. No, not enough oxygen. The air is too thin to breathe, and the average temperature is about minus 90 degrees freezing up there. Thermosphere, the warmest layer of them all. The temperature at the top of this layer is around 2,000 degrees Celsius, 3,632 degrees Fahrenheit, decreasing as you descend. So as you come down, the temperature will decrease. O2 molecules absorbs a lot of solar energy. There are so few molecules that they can travel as far as 1 kilometer before hitting each other. That is pretty far compared to down on the surface, a millionth of a centimeter before molecules run into each other. So that's basically nothing. So top of this layer is called the exosphere, and molecules can't escape out into space. Ionosphere, different changes with the daytime and night. The sun's energy causes a low layer to form during the day. Radio signals are absorbed and weakened in this region. The signal doesn't travel very far at night. The layer disappears and the signal can travel further. So the ionosphere, if you look at the chart, it is pretty far down there, about where the stratosphere is, almost equal with the layer of the stratosphere. And then, like I said, depending on the stability, daytime, nighttime, what radio waves, how far they can transmit out. Alright, that is all for this. My next video, I'm going to do a warming of the Earth. I guess no global warming or anything like that. We're just going to do a incoming solar radiation, how the Earth heats, and how that affects the different latitudes, and then causes maybe different pressures, winds, circulation of the Earth. So, alright, if you learned anything from this video, just give me a thumbs up. Like this video, share this video. Let's get this out here, and I'll keep them coming. Thanks for watching. And don't forget to visit Meteorology101.com. A lot of information on there, goes way deeper into detail. Atmospheric structure is the different atmospheric layers of the atmosphere of different planets, the sun, and goes way more in depth on compositions of the atmospheres. Meteorology101.com, just that junior website is just a blog site. Several categories there you can click through to just learn pretty much anything you want. Jet stream formation, pretty much all the details. We're going to start covering in the videos. I'm starting basically a basic video series. I know I've kind of zipped through it pretty fast. I'll try to slow down, get a little bit more information in here. I'll try not to get these videos going too long though. So if you like the video, let me know. Leave a comment, and if I need to go a little bit longer, a little bit more detail, I need to slow down, critique it. Go ahead and comment on it, and don't forget to share. Thanks for watching.